Hello everyone. Last episode we got a bit sidetracked creating the logic for this little display here, which just takes whatever binary data we have and translates it into a more human-friendly format. I think it's going to have been worth the effort though, because now when we work with things like the 4-bit register that we built a while back, we're able to actually see what data is stored inside of it. So if we input 1001 for instance, and then enable the store signal and pulse the clock, we can see the value 9 showing up over here. Now, what I'd like to experiment with and try figure out today is how we're going to handle taking data like this and moving it around inside our little simulated computer so that different components are all able to talk to one another. So I've added in a second register here, and I'm just going to finish connecting it up to the inputs and the clock signal quickly. We can then give it its own store signal so that we can put whatever value we want in there. Let's maybe do 0110 this time, and I'll turn on the store signal, pulse the clock, and there we have it. But now, what about transferring data between the registers? For example, say we want to be able to take whatever's stored in this first register and copy it into the second. In that case, this register would be receiving data from two different places, and so we'd need some way of selecting whichever data source we're interested in at the moment. We have actually done something like this before. If we just open up one of these 4-bit registers, and then open up one of the 1-bit registers inside, you might recall this little construction we made. As we can see, this takes in two separate sources of data. There's the current value stored in the flip-flop coming in here, and there's the input value coming in over here. Then if this store signal is off, we can see that the first data source is selected and the second source is ignored. And the opposite would be true if the store signal was on. So this is called a data selector or a multiplexer, and let's quickly make a version of this that selects between two 4-bit values instead. So we can again just use an AND gate, well 4 of them this time, to zero out the first data source if the select signal is not off, and another 4 to zero out the second data source if the select signal is off. We then simply OR together the corresponding bits from the two sources and output the result. That should work, but let's be thorough and test it quickly. So I'll put 1001 on this first input and 0110 on the second. And now using the select signal, we can see that we're able to choose which of those we want going through to the output. So super simple, but extremely useful. Alright, we can now head back to our two registers here, and let's bring in our new multiplexer chip. We can then connect up the output from register A as the first 4-bit input, and this data here as the second 4-bit input. Finally, of course, we'll need a new control signal for choosing which of those two sources should be selected. With that all set up, we should be able to copy the 9 that's currently stored in register A over into register B, and so let's quickly try pulsing the clock, and that seems to have worked. Of course, we can still store whatever data we want directly into B, simply by changing the select signal and running the clock again. So using a multiplexer like this is one way we could handle the transfer of data between different components, but there's a bit of a problem. Imagine we have just 4 components, each of which needs to be able to receive data from any of the other 3. We could build a slightly larger version of our multiplexer to handle this, so here the other 3 chips would all send their data to chip A, and there'd be some selection signals to choose between those, which I've left out here just for simplicity. Then of course chip B wants access to all that data as well, so it could have its own multiplexer, and same goes for chip C and D as well. The problem with this approach really is just the obscene amount of wires we're going to have running all over the place. And while it's conceptually very simple, I think it might end up being a bit confusing to keep track of what's going on. So it'd definitely be nice if we could use a more minimalistic approach. What we could try doing instead is creating a set of shared wires for transferring data called a bus. These bus lines can run through the computer wherever they're needed, and any of the chips can read data from the bus or write data onto the bus for anyone else to read. One slight caveat there though is that while all the chips can read from the bus simultaneously, only one chip can actually write data to the bus at a time, otherwise there's going to be conflicting data, and we'll look into that a bit more in a minute. One solution to this problem would be to use a multiplexer. We could have one big one over here, and instead of any of the chips writing to the bus directly, they could all send their outputs to the multiplexer, which would permit only one of the data sources onto the bus at a time. Since there are 4 sources to choose from here, we'd need 2 selection signals to cover all the possibilities, and let's just wire those up quickly, and then output the result onto the bus. Currently, the data from chip C is going onto the bus. I wired them up in a bit of a strange order, but anyway, we could change the selection signal here to let the output from chip A through instead, or from chip B, or lastly from chip D. This is a good solution, I'd say, but it is a bit awkward that we have to run all our wires to this giant multiplexer. It would be really nice, at least in terms of keeping our wires tidy, if each chip could just put its data onto the bus right where it is. To better understand the problem with this, and how we might get around it, I'd like to venture out into the real world for a moment and take a look at this little 4-bit register. Looking at its datasheet, we have power and ground pins of course, and then these here are our 4 data input and output pins. There's also a clock input over here, and a reset input here, which we don't have in our simulated version, but it just clears the data to 0. Then at the bottom, somewhat confusingly, we have these 2 pins together making up the store signal. They both need to be 0 in order for the store signal to be on, and I'm sure there's a good reason for that, but I have no idea what it is. Finally, at the top are these 2 inputs, which, like the store signal, are really just a single input, and what it does, well, we'll get there in a minute. First of all though, I've got some wiring to do. Hopefully I'm setting this up okay. My grasp on this stuff is still extremely tenuous. I've been thinking though about making some sort of series to explore the world of electronics in more depth, because I do find it extremely fascinating. So let me know if that sounds at all interesting. In any case, I've finished setting this up here, so let's now use these tiny switches to enter some data. Then I've set the store signal to just always be enabled for this example, so all we need to do is make the clock signal go from low to high, and we can see that our data has been loaded into the register. Just to fully test that this is working though, let's try entering something else, like 0110, and clock that in. Alright, that's looking good. So now the first thing I want to do here is just quickly remind ourselves what these 1s and 0s we're working with all the time actually represent. These little green LEDs are all connected to ground at the top, so the ones that are on must have been electrically connected to the power pin inside the chip, meaning that a 1 just represents a connection to a high voltage, somewhere around 5 volts in this case. On the other hand then, a 0 represents a connection to a low voltage, something at least close to 0 volts. So I'd imagine that the lights that are off should be connected to the ground pin inside of the chip. We can confirm if that's actually the case by just grabbing one of the lights that's off and turning it around to connect to the power rail up here instead, and we can see it does light up, so it must be connected to ground on the other end. This kind of output is called a push-pull output, because by connecting to power for a 1 or ground for a 0, it allows current to flow in either direction, which I guess is kind of like pushing and pulling electrons. There are other types of outputs with various trade-offs, but let's just focus on this kind for today. So returning to the simulation for a moment, let's say we have some chip that's outputting a 1 onto the bus, which as we've just seen is essentially connecting it to its power pin, and another chip that's outputting a 0 onto the bus, essentially connecting it to its ground pin. What we have now is a very low resistance path between the two, which means that we'll get an excessive amount of current flowing, potentially damaging some components and causing glitches due to unexpected data on the bus. This undesirable state is called a bus contention, and in the simulation it's just represented with an annoying flickering to show that something's gone wrong and the bus doesn't know what value it's supposed to be. To solve this problem, let's return to our mystery input over here. All this does is simply allow us to control whether the outputs are enabled or not. So I've wired up this button on the left to act as a disable outputs button, and if I press that, we can see that all the lights turn off. Inside of the chip, all the outputs which previously were connected to either power or ground become essentially disconnected instead. This third possible state, neither 1 nor 0, goes by different names such as floating or high impedance or tri-stated, but the point is that if these outputs were connected to a bus, they would no longer be having any effect on it, and so some other chip would now be free to put its data onto the bus instead. I'd like to take a very quick look at how this works. So imagine that this here is one of the outputs from our chip. The basic idea is that internally the output is connected to 2 transistors. Then if the chip wants to output a 1, there'd be some logic to turn on this transistor here, which provides a connection to the power pin. On the other hand, if the chip wants to output a 0, it would turn on the other transistor, which provides a connection to the ground pin. Finally, if the chip is asked to disable its outputs, then it will just make sure that neither transistor is on, which means that the output is effectively disconnected, because when the transistors are off, they're going to be extremely reluctant to let any current flow through them. Just to demonstrate this a bit better, because 0 and disconnected look exactly the same here, let's imagine that our output isn't going to a light, but rather to the input of some other chip. Now, what can happen in this disconnected state is that some sort of electrical noise can come along and interfere with that input, causing it to randomly float from 0 to 1 or vice versa. If we're outputting a 0 here though, for example, we can see that that little bit of noise is no longer able to interfere with the input, because we're providing this strong connection to ground. Alright, hopefully that makes some sort of sense, but in any case, let's head back to the simulation, where I've quickly programmed in a new type of built-in chip called a tri-state buffer. With this, we can connect up an input and an enable signal, and all this does is output whatever value it receives as input, so either 0 or 1. Unless, of course, the enabled signal is turned off, in which case it goes into this third disconnected state that I've been harping on about. So just for convenience, let's make a little chip that has an output enable signal, along with 4 data inputs, which it can then pass through 4 of these new tri-state buffers. I'll then wire up the output enable signal to each of the buffers, and then of course wire up their outputs. This just gives us a nice easy way to take our nibble, which is the name for half a byte or 4 bits of data, and disable it or enable it, depending on whether we want it going onto the bus or not. So let's save this chip quickly, and we can maybe just call it our bus buffer. Then going back to our little test here, let's try using that to replace this one big multiplexer, so we can see which approach we like better. Now, instead of these 2 selection signals, we're going to need an output enable signal for each chip, so that is going to require some extra wires, but on the bright side, it'll at least be possible to give them meaningful names now. I know I've put these in a bit of a strange order here, but I just wanted to be able to connect them up without getting too many wires crossed. Anyway, let's try this out quickly. So starting at the bottom, I'll enable the output of chip B. Then let's switch to D, and then C, and finally chip A. So that's looking pretty good, I'd say. Although one potential pitfall with this approach is that, unlike with the multiplexer, we could mess up and have multiple chips trying to output their data simultaneously. Related to that, when I was reading the datasheet of that 4-bit register we were playing with, I was interested to learn that it was designed so that disabling the outputs would take effect slightly more quickly than enabling them, to minimize the chance of a conflict. Thankfully, we don't have to worry about any of these subtle timing considerations from the safety of our simulation. So let's try working with this three-state bus approach, because I think it's going to make it a lot easier to stay organized, especially in the future if we're working with more than just a handful of chips. I'd like to test this setup with our actual chips though, so I've set up some inputs over here, starting with 4 data inputs, then some output enable signals, some other control signals, and finally the clock. Let's create a 4-bit bus quickly, and then we can grab one of our buffers and use it to allow this incoming data here onto the bus if the data output signal is enabled. Then let's also bring in 2 4-bit registers, which can get their data from the bus, and also put data out onto the bus. Then to do some simple maths, let's bring in our little ALU. Now this is a bit awkward because it takes in 2 4-bit numbers, so instead of using the bus, let's make an exception here and just let it get its inputs directly from our 2 registers. It can then put the result out onto the bus though. Okay, there are just a few control signals that need to be wired up, so I'll do that quickly. We're almost running out of workspace here already, so I'm going to have to make some more upgrades to the program soon, but I'll worry about that later. For now, let's just connect the clock to our 2 registers, and then it's time to see if this works. So we can enter some data and output it onto the bus. Then let's tell register A to store that value and pulse the clock so that it actually happens. Alright, then let's maybe try using our ALU to add the contents of the 2 registers together and store the result in register B here. So first of all, let's make sure that only the ALU is allowed to put its data on the bus. We can then tell register B to store whatever value is currently on the bus, and then to make that happen, let's pulse the clock again. Alright, so we've just solved the very complex math problem 3 plus 0. Thrilling stuff. Let's run the clock a few more times to just keep adding the value in register A to the value in register B. Okay, we've ended up with 15 in here, and now I want to try copying this value into register A. So let's set that up quickly. We want the output from register B on the bus, we want to store it in register A, and finally, as always, we'll pulse the clock. Everything seems to be working, which is nice, but for completeness, let's also try storing a value, perhaps 0110, directly into the B register. And we can see the value 6 has shown up in there. As a final test, I'd like to try subtracting this value in B from the value in A, and then storing the result of that calculation into register A. To do that, we'll want the output from the ALU on the bus again, and we'll need to tell it to perform subtraction this time. Then we want that result stored in register A, and with that set up, let's pulse the clock one last time. And there we have our answer. So we've managed to build possibly the least powerful and most annoying to use calculator in the world, meaning things can only improve from here. That's all for today though, so until next time, cheers.